Don't start your presentation. Fine. So please come late. Second chair, and with you behind you, like a V.
Okay.
Yeah, behind you. Yeah, like this. And then you get your diploma, probably from your promoter sitting over there. You can stand a little bit, yeah. Then I will say you may all sit down, except the two of you, you are staying here until the end. So until the services, you may now sit not me, clear?
Yes.
Then we will all leave. Is someone going to make pictures?
Well, I mean, I will ask definitely somebody to make pictures.
Then please do it now because we need a photographer to make some pictures at the stairs and then they sign the diploma.
Okay.
Later, now you think, oh yeah, so later on it will be nice.
So, may I just make it clear? So now I just need to ask the person who will make a picture to be ready.
So
right after you.
if you know who's going to make pictures, then I have to explain a few rules to you. So if you can ask your family to sit next to you and also wait after taking at the stairs, I'll ask someone this one. I asked the partner in because if you're standing there, you have nothing. It's that knife. Beginning, yes. So ask your family to come and sit over here. Okay, your mother and your sister? Shake hands.
Okay, it's already quite time. First of all, it's lovely to have all of you here and my PhD defense. I think that first I need to explain you what is my research about, but apparently my research is very theoretical and I would consider it very boring. So I will just explain one of the motivations for things which I was doing for past 4 years. So assume you have a body, and for this body, you want to know the evolution of temperature within time, let's say, in a certain time period. How high is it, the maximum, or perhaps a certain function of this body? Well, you can use many, many methods. So this perhaps the simplest one to measure whether the temperature is good enough. This might be more precise, but the thermometer tells you H, so it's too hot, which is perhaps also fine. Well, or, which is also a good method sometimes, you just measure temperature in the surrounding of your body, and the mean of temperature in the surrounding of your body approximates the temperature of your body. So this is also fine. But unfortunately, some of these methods are not accurate enough. And also, unfortunately, they do not provide you with the temperature inside the body. Luckily, in physics and mathematics, there is a certain mathematical model which helps you to actually understand the evolution of temperature within time, within the whole body. It's called the heat equation. So here U is temperature. It's a temperature function. It's a function of the body. Well, we also have some boundary conditions, obviously, in our case, but I will omit this. And this explains the evolution. du equals delta u dt. So here the point is that dt is difference in time, and delta u tells you somehow the difference between the mean temperature in the neighborhood of the body and the temperature in this point. So say in the neighborhood you have the mean temperature higher than the temperature in this point, then the temperature in this point will become higher. Or if the mean in the surrounding is lower, then the temperature in the point will become lower. So this, what exactly this strange thing, Laplacian U, means, so to say, physically. But unfortunately, our life is not so nice. I mean, it would be great if all our mathematical models would work well. And in general, we have some additional noise which pops up from something. In this case, we will consider a certain noise. Here, this is our noise. Here, I took this noise, just a certain Google search stats on Nicolas Cage. So this is our noise coming from Nicolas Cage. And this noise is random. So random means that you can't predict this noise beforehand, means that you can't predict now the whole noise for the whole time of the universe somehow, for the whole R+. You can't go as far as you wish. And this what means random or stochastic. Any such noise can be decomposed into two parts. The first part is predictable, means that you can predict it perhaps not like a day before, but 5 seconds before. Say, if you hit something, you know that something will become hotter. This is something you can predict. But the second thing is a martingale. A martingale is a process such that given information today, the best approximation for tomorrow is the process itself today. Say you sit in a room and you have no news, you have only stats on Nicolas Cage, which comes up every 6 minutes, as here. And as you don't know any information, I will ask you, in the next 6 minutes, how many people will look for Nicolas Cage? What you will tell? Well, approximately like the same number as now. This will be the best approximation for the search stats within the next 6 minutes, given you don't have any information on Nicolas Cage. So this is a martingale. If you know that Nicolas Cage is shooting a movie now, then you know, well, it will be approximately 10% more, or 15 or 20% more. But then what is important is that the difference between this 10% more and now, it also can be decomposed in this predictable part. It's exactly your 10%, and this martingale. So this is explain the whole decomposition somehow, how it comes up. And therefore, we have a stochastic heat equation. So it has some. Here our predictable part and our martingale, and f at g sort of measure how big is impact of this noise. Whether it's too big, I think that in this case it's almost negligible. So because I don't think that Nicolas Cage somehow impacts your heating, but in general it could impact. And now let's ask a more general question. So very often very often you need to know some characteristics for your function, for a temperature function, like maximum or perhaps a mean of a certain function of this function to the power p, or perhaps certain mean of function phi of this function, or perhaps different means on different parts of your body, and so on. So actually, families of such functions, they are called Banach spaces. So a Banach space is family of functions satisfying one of these properties. Well, it's a bit more general, but for this presentation, I think that this is enough. And then, if you're interested in these particular characteristics of your temperature, then you just can translate your SPD in a stochastic evolution equation by considering an x-valued process. So you consider your initial temperature to be a certain function from x, and your evolution now is in x-valued, is x-valued. So it's du, it's x-valued. This delta u means something different, but still x-valued. And now you have this f and g also x-valued. And the point is that if you want to solve such an equation, you will need to make meaning of integrals with respect to this predictable part and martingales of x-valued integrands. And if for this predictable part, it's very often quite simple, because your A has bound variation, so it's in general quite simple. Then for martingale, it's quite tricky. And this is what was part of my research during my PhD, defining a stochastic integral of a Banach space value thing with respect to a martingale, as well as some properties of martingales with values in Banach spaces. This is what I was doing. Yeah, thank you very much, and yeah, not only for coming and for your attention, but also for being so great for past 4 years. Thanks. Okay. Okay.
Yeah, this was fine. I didn't realize they hadn't defined these martingale
Or somewhere here.
Over here.
Als je begint is het wel een beetje zeker. Als je één keer zakt,
One, two, three.
really funny. I mean, you should look at the whole. Just 10 seconds.
Wilt u opstaan? Gaat u zitten.
Ik open de zitting van de commissie ter beoordeling van het proefschrift en de stellingen van Ivan Yaroslavtsev. De verdediging zal in het Engels worden gevoerd. I request the promovendus to go to the lectern together with his paronyms. A warm welcome for all of you at the public defense by the candidate of the dissertation entitled Martingales and Stochastic Calculus in Banach Spaces. The board for doctorates of the TU Delft has installed a committee to evaluate the dissertation and propositions. The committee will have a debate with the candidate in public. It is an honor to present the members of this committee, to whom I extend a hearty welcome. Professor Geis, University of Jyväskylä in Finland. Professor Osekowski, University of Warsaw in Poland. Welcome. Professor Dirksen from Aachen RWTH Universiteit in Germany. Welcome. Professor Kator, Radboud Universiteit Nijmegen. Welcome. And from TU Delft, Professor Jongbloed. And the promotores, Professor van Neerven and Professor Veraar. Thank you all for taking part in this academic ceremony. My name is Bart van Aarem. It is my pleasure to chair this session on behalf of the Rector Magnificus. I would like now to start the opposition, and I give the word to Professor Geis. Professor Geis, will you start the opposition?
Ware promovendus. I was impressed about your thesis. It is difficult to ask questions about this amount of articles, so I have to make a selection of these questions. And I, in a way, have a question about an article which does not explicitly relate to UMD spaces, but I assume it's about UMD spaces implicitly. So this is your work about LQ-valued Burkholder-Rosenthal inequalities. And your main theorem works for functions which have values in LP spaces or LQ spaces. And my question, the natural question is, if you look also at the last parts of your doctoral thesis where you consider lattices with the UMD property, is it possible to replace that LQ condition by a Banach's lattice which has a certain concavity or convexity? And in the opposite way, if you would assume something like that, would you recover the convexity or the concavity of this Banach lattice space? Would you see a chance to extend this part of this thesis to a more general class of Banach spaces?
Waarde promovendus. It's a long question, but is the question clear to you? You can defend yourself.
Yes. Yes. Yes, yes. What is a particular structure from your point of view that you have to use the LQ structure, that the explicit Banach lattice structure, which makes it different from a general Banach lattice? So what is the particular structure of that LQ which is used?
Turn on the microphone. I'm sorry. Yes, so another thing actually, what was also important, we needed called the Rosenthal type inequalities. This is what was it based on.
Yeah.
And that inequalities were reached only for LQ spaces. And one of the points why it could not be perhaps extended. One second, please.
I think you do decoupling, then you use.
Yeah, this is also one of the points. Yes, but also I think, if I'm not mistaken, they were also used some mixed, not mixed, but LQ over 2 and LP over 2 spaces. So there are certain restrictions which might be omitted. But the most strongest restriction which I see so far is this using of non-commutative LQ spaces, so to say. This is the most difficult. The others might be omitted given your Orlich function, say, is within your delta to enable two conditions are within certain range you want, like within 2 NP, or strictly bigger than maximum of 2 NP, or strictly less than minimum of 2 NP.
Would you think if you're asking the other way around, you would assume a Banach lattice such that you have your result, or one part of the results? Do you think that by the choice of particular processes you plug in, you would need to recover that a certain convexity or concavity is needed? So just going that that your results are in a way sharp, so that you can go the other way around as well?
Yeah, first of all, you always recover the UMD property. This is, I think, this is what always, always happen, because if you plug in certain indices like plus minus ones, then your compensator doesn't change actually. Your compensator measure, and so you will have certain that a certain martingale transform is bounded in LP, which is very often the case that you have the UMD property. I'm not sure that you can recover more than that. Well, I think so.
Another technical question before I have my last general question. There's a restriction of this parameter range. You exclude that 1, p equals 1, in this because you would like to have reflexivity. And but do you think that some of your results that there's an analog for p equals 1? That could you comment on that? If there's a minimal chance to get something like that there? Or?
The opponent, this is a very good question. So first of all, for p equals 1, you have upper bounds. And this is also very, I think, very useful. And I think that there is actually a hope that you can have an equivalence for p equals 1 because of general structure, let's say, of because there is Gaussian inequalities which hold also for p equals 1. So you might hope that even this predictable, because there's Gaussian inequalities for integrals, also would hold for p equals 1. And I think that this also could be true because such type of inequalities with the predictable right-hand side for a general EMD space are possible. And you know that the right-hand side then will be a certain predictable process. And then this is a matter of, it might be very technical, but it could be that this predictable process coincides with exactly one has in this case, p equals 1 and q within 1 infinity, excluding 1 infinity.
Thank you. There's 1 minute for one short question?
Yes.
Yeah.
Small question, short answer, hopefully.
Yeah. What would you see as the main open problems? Because the thesis is mainly about UMD spaces. And what would you say, what are the main open problems if you would supervise yourself, a PhD student? What would you say to him? This is the main problems that are open in that theory of UMD spaces. Do you have some list of problems you would rank?
Yeah. Many thanks for this question. So there is one open problem which I tried to solve a couple or 3 or 4 times in my life. Also with you once. So this is a problem on comparison of the UMD constant and the norm of the Hilbert transform on the comparison. And that one I would consider as it's as the most important, perhaps not from the practical point of view, but from the theoretical point of view, in actually understanding what happens with orthogonal martingales and why, and is there this some analog of orthogonal martingales in discrete setting, somehow, whether you can go from orthogonal martingales to discrete setting. So I think that if one would solve such a problem, one would provide us with a really great technique to work in general with the EMD balanced space valued things. Also, there are a lot of questions about stochastic integration, whether you can provide, which type of estimates you can provide for stochastic integrals, which equivalences. There are several of them, and this I think also one of the biggest problems.
Thank you. We still have challenges ahead of us. Professor Geis, are you satisfied with the answers to your questions?
Yes, I'm satisfied.
Thank you for your opposition. I would like now to continue the opposition, and I would like to invite Professor Ossakowski to do the opposition.
Parde promovendus. So my first question concerns Burkholder-Rosenthal inequalities. In the literature, a lot of work has been done to understand the behavior of the constants in Burkholder-Rosenthal inequalities. So there are these classical works. So my first question is whether in your works on this LQ valued case, have you obtained some what can be said about the behavior of these constants in this Banach setting?
Hopefully the opponent. Thank you very much for the question. So we had some discussion on this, on these optimal constants, and if I remember correctly, we left it as not an open problem, but an interesting open problem for the reader. But the order of the constants which we get using, for instance, the techniques like the canonical decomposition or decoupling altogether, I think this order would be something like beta cubed or beta squared, which I think quite far from an optimal one. Because in the real world case, this question was studied very well, if I understand correctly.
Real valued case, this is below the linear, yeah.
Yeah, and then for a Q case, I think that let me open it again. Just a quick look, because we had a remark on this actually. No, it's not here. Yeah, I'll just show you the remark, the audience. So it's remark number 734. And, okay. And, well, this remark is, we study such type of questions like which constants can you get? And in the very end of this remark, you can see that it should be mentioned that the dependence on P and Q in 716, it's the main result, and we call it the Rosenthal inequalities, is not optimal. So we'll leave it to the reader. So this remains open in this particular case.
Okay, so I will turn to the next question. The next question concerns the behavior of some singular integral operators. So I will specify it to Riesz transforms.
Mm-hmm.
So using the martingale techniques, what can be said about the behavior of the first order and second order Riesz transforms in the UMD context? I mean, what can be said about the behavior of the LP constants? What can you extract from these martingale inequalities? First order and second order.
Many thanks. First start me with the first order. So the actual order of a second order. The actual order of the LP norm of the second order Riesz transform in the UMD setting was actually shown in 2010 by Geisman, Goring-Smith, and Saxman. And it's known that it's of order beta px. And you can actually prove that its norm equals the norm of the martingale transform, which is given by numbers 0 and 1. Not -1 and 1, which you have in the UMD setting, but 0 and 1. This norm will coincide with the norm of the second order Riesz transform. And for the first order Riesz transform, as for me, I'm not sure, but as for me, it should coincide with the Hilbert transform norm. Am I correct? Or this should be true. I think that this should be true. And in this case, the best order we know in terms of beta, it's unfortunately due to the result of Garlin and Buchholder in 1980s, that then the norm of the Hilbert transform is within the square root of beta and beta squared. So, and this is, as I told before, this is an open problem, whether you have any type of linear dependence between these constants.
And so this result for a second-order Riesz transforms, does it follow from your results for the Fourier multipliers, for these Levy multipliers you study?
It follows from that as well.
Right, because you study these estimates for these pure jump martingales, right? So
there you have exactly this, yes. So you construct a special Bandman function, which must be quite close to you, which is not zigzag concave, but you can call it like 0-1 concave. So it's then you allow less concavity, so to say, and this function actually generated by the martingale transforms I told you, by 0-1 martingale transform, and then by using this function for these Levy multipliers, you will get the result. Yes, you will get the. But as I told you, you can also use the technique of Geismar, and Saxman. It also works well. Then with the same type of martingale transform, you get exactly the same result. So there are several ways actually to prove this result, and this coincides, to be honest, with the LP norm of getting a particular part of the canonical decomposition. All these norms coincide.
So my last question. Much of your thesis is devoted to LP estimates in the UMD context. So my question is, what can we say in this, let's say, very general context? What can we say about weak type 1-1 estimates for, let's say, for continuous time martingales with values in Banach spaces? What can we say?
I was expecting from you this question. So you can, for discrete case, you can prove that you will have the same type of weak 1-1 estimate you have for a martingale transform. So it's like 2 over zeta in 0,0, where zeta is a zeta function, not the famous one, but the zeta function from Buchfelder. So this is what you can do in the discrete case. And with the continuous time case, you need to decompose, and this is something we did as well. We need to decompose your martingale, if you have a weak differential subordination, into a part which is orthogonal and a part which is not orthogonal, but say anti-orthogonal, so to say. And for this anti-orthogonal part, you also have this 2 over zeta 0,0, the same constant. And for an orthogonal part, you need to use a plurisubharmonic function for weak 1-1 transform. And then there are some little problems. The sharp constant, I believe, should be the same like for discrete transform, but for this plurisubharmonic function. But there are some, as I told, some technical problems because it's not a norm. So this function is not convex, for which you use in weak 1-1, right? So you can prove some estimate with some constant over this function in 0, but this constant is a bit big because you go to a space which has a norm, right? So use some equivalence with some Banach spaces. There you do all the job and go back, which is not nice. So I'm working on it and see what happens. So, so to say. But so far, this is what I know.
Okay.
Professor Ossakowski, are you satisfied with the answers to your questions?
Yes, I am. Yes.
Thank you for your opposition. Next in opposition is Professor Dirksen. Professor Dirksen, can you continue the opposition, please?
Waarde promovendus, dear Ivan, I would first of all like to congratulate you on the impressive thesis that you've written, which contains many results that enhance our understanding of martingales in UMD Banach spaces.
Thanks.
As a first topic that I would like to discuss with you is the Burkholder-Davis-Gundy inequalities that you proved. I saw two versions in your thesis. The first one is valid for UMD Banach function spaces in chapter 8. The second one in general UMD spaces.
Yeah.
They have a slightly different form, however, and I was wondering whether chapter 9 makes chapter 8 obsolete in the sense that there's a direct way to derive the result in chapter 8 from the one in chapter 9. For discrete time martingales, this is sort of clear. I was wondering whether you could comment on this.
Hochgelir, the opponent, thank you very much for this question and for all the words you told, all the warm words from you. So actually, and this is a bit funny, in chapter 9 there is even a certain extended version of chapter 8 is proven. So in the very end, so in chapter 8, in my work with Marc Ferrat, we were able only to prove it for p strictly bigger than 1. And chapter 9 sort of helped me to extend this result to p equals 1 as well. This is the first thing. The second thing is that I think that it's actually quite direct. Chapter 8 could be actually quite directly proven using chapter 9 by using the fact that the gamma norm coincides with the square function for a Hilbert space, if I'm not mistaken. Not coincides, but they're comparable. Yeah. So the norm in this of a square function. Yes. Yes. And then I think that yes. Then it would lead, I think, automatically. But what was a problem actually in chapter 9 is proving existence of pointwise martingale in the Banach function space for a general martingale, and therefore it was quite a work in chapter 9, in chapter 8, and also in chapter 9 of proving existence of such a pointwise version.
Okay, so the short answer is yes.
I gave as full answer as I could. So,
okay.
Yeah.
All right. I would like to ask a question. Meneer de rector, this question concerns proposition number 2.
Thank you. And it's a good tradition that the paradigms reads out the proposition.
Proposition number 2. In particular, with differential subordination, the canonical composition, look for the Descartes inequalities, and stochastic integration makes sense only in the backspace.
All right, I have some trouble with part of this statement. So part of this statement reads, stochastic integration makes sense and exists only in UMD Banach spaces.
Yes.
So I tend to disagree with this statement because, for example, you can define weak stochastic integrals in more general settings.
Yes.
And even if you're interested in norm estimates, for example, if you have an integrator that has independent increments, there's stuff that you can do outside of UMD spaces by, let's say, using decoupling, right? Could you comment on what you exactly mean here with the statement in the proposition?
Many thanks. Very good question. So the point is that proposition shouldn't be too long. I could put there sharp LP estimate for stochastic integrals. Makes sense on the UMD Banach spaces, but this is the first part which I left. But you're extremely correct. In many cases, you can provide upper estimates for independent increments, for Brownian motion and the deterministic integrand, for Poisson random measures and some martingale type 2 things, and also for Wiener noise, for many cases outside the UMD case, and even here, some case somewhere L1 is also covered, right? For instance, for the Rosenthal inequalities, L1 is covered, some upper estimates. So yeah, first, this is a good remark and good question, and second, I meant on the sharp LP estimates, which are apparently possible only in UMD Banach spaces. Equivalence, so to say.
Is this something that you can prove, or is this sort of like a philosophical statement or conjecture?
In some sense, you can prove it. If you take, say, Brownian noise, right, and you want your LP estimates to be sharp, you want to have equivalence, then you will have this equivalence if and only if you have the UMD property due to the two-sided decoupling. It's possible if and only if X has UMD property. The same you can do actually for compensated Poisson, for instance. You can also prove that it's possible if and only if X has the UMD property. So also you have some BDG inequality for discrete case, which are in some sense possible if and only if X has a UMD property. So many of these things, whenever you can plug in a sign, and then you have a sharp estimate, you will get something which is possible if and only if x is UMD, or only if x is UMD, right? So this is the whole point. And whenever you have an estimate for a stochastic integral, so that you can plug in a sign, then yes, then it will imply UMD. So.
Okay, I would like to ask a final question. So the Burkholder-Davis-Gundy inequalities that you prove in the last chapter are very general, but they sort of have a downside in the sense that, let's say, the right-hand side that you get in these inequalities is not predictable. And on the other hand, you have some replacement of that with a predictable right-hand side in chapter 7.
Yes.
But this is only valid in LQ spaces.
Yes.
So I would like to ask a twofold question. So first of all, do you think that using the techniques that are already in your thesis, you could extend these Burkholder-Rosenthal type inequalities in chapter 7 to some spaces that are interesting for the study of SPDEs, like Biesov type spaces? Mm-hmm. And then secondly, sort of going beyond that, I would like to ask the Holy Grail question. Do you have any conjecture on what a generalization of Burkholder-Rosenthal might look like in UMD Banach spaces?
Yeah. Thanks. It's a very good question. I think that, unfortunately, I need to start with the second one rather than with the first one. So the second question has an answer yes for continuous time martingales. So it's a certain extension of Burkholder-Davis-Gundy inequalities, but with a predictable right-hand side somehow. And it goes back to works of Kallenbeck, Vapien, Wojcinski, and many other people on local characteristics of a martingale. So if you have a pen, it would be nice. No, I don't have a pen. Okay. Oh, many thanks. Many thanks. So if you have a martingale, M, then due to one of the parts of my thesis, you can always decompose it in a purely discontinuous martingale and a continuous martingale, if and only if X has the UMD property. So then, local characteristic of your martingale is the following pair. It's a quadratic variation of a continuous part. The quadratic variation process, recall that this is a bilinear form-valued quadratic variation process. And a compensator measure of jumps of a purely discontinuous part. So nu MD is a compensator of mu MD, of a measure generated by jumps of your purely discontinuous part. So what seems to be correct, so this is called local or Grigorionis characteristics. Local Grigorionis characteristics. Yeah. And then what seems to be true, but this still needs some work to prove it, is the following statement. It's, as I told, it's an extension of some theorems of Kallenbeck and Kvapien and Wojcinski and Hitchenko. So theorem or conjecture, I would say it, so there are still some empty places which I need to fill in, is as follows. If M and N have the same local characteristics, then for any P between 1 infinity, expectation of supremum of the norm of MT to the power P is equivalent to the expectation of supremum in T of NT to the power P. And if you remember, for instance, for martingales, for LQ-valued martingales in chapter 7, what we had an expression of the norm exactly in terms of these local characteristics. This is what we had. So this is I think, a general way how to look at them, at this predictable path. That this should be a path depending on these local characteristics. So this is the answer for your second question, I think.
Professor Dirksen, are you satisfied with this answer?
I am.
There's plenty of opportunity to for further discussion later. Thank you very much for your opposition. I would like now to invite Professor Kator to continue the opposition.
Waarde promovendus, I would also like to congratulate you on your work.
Many thanks.
It's very impressive amount of results, and also groundbreaking, I think, in this field. I'm not an analyst. I'm more of a probabilist and a statistician. So when I was reading this all the time, I was thinking, how could I use these results in my work? And from that thought, a couple of questions arose, and I would like to ask you about this. So my first question is about why are we looking at these martingales in these very abstract Banach spaces? And then you don't spend a lot of time on explaining this, but you do say that stochastic partial differential equations are an important reason why this is relevant. And then I was thinking that for partial differential equations, distributions are often important. You use them in the weak solutions of partial differential equations. So if you look at the space of, let's say, Schwarz distributions, this is not a Banach space, it's a nuclear space. No. Would it make sense to look at martingales in these spaces, and with your methods, could they shed any light on that?
Hooggeleerde opponent, thank you for your questions and for what you told. So the first thing is that what was actually of interest for my thesis was LP estimates. And for instance, for Schwarz space, it's a locally convex space. And this is a good question somehow, whether you can go, what you can do in locally convex spaces, what type of estimates. But I think that you need to use like different methods. You need to use perhaps some type of cylindrical martingale theory or something like that. Because you have a family of linear functionals which you want to bound, if I understand correctly. So this is a bit far from this Schwarz space thing. Concerning your question about motivation, so one of the original motivations indeed goes back to SPDs, which can be translated as stochastic evolution equations with values in some Sobolev or Besov spaces. And all this, if those spaces are reflexive, they have some geometrical structure which actually plays a role in stochastic integration theory. So in many cases, it's much simpler to go to this one geometrical property and prove everything for this one geometrical property, and then go back to your particular Banach space you have. So this, I would say, this is how it goes, I think.
Okay, thank you. So another thought that occurred to me as a statistician is martingales are also used to extend the central limit theorem in statistics. Instead of independence, you use martingale structure, and then you can still use a central limit type theorem. Would that also be possible for martingales in UMD spaces?
It might be possible. I'm not sure, but but it might be possible because I'm not a big expert in central limit theorem, so to say, and not such a big expert in statistics. But it might be that some of statistical methods, if you want to extend this to Banach spaces, then you will need some properties of a Banach space, and then perhaps not UMD Banach spaces, but some other Banach spaces will play a huge role. I'm not sure which exactly, but this is what happens at least with this abstract theory, that you need some geometrical properties for a real valid thing. You don't realize when you work with this real valid thing, but when you extend, you realize that you need such an inequality or such an equivalence. And the same could happen with the central limit theorem and such type of theorems you have in statistics and in probability.
But you do not know about this.
But I'm saying, I don't know what exactly plays an important role when you extend it to a Banach space valid situation, which type of inequality. There should be some, but this is a bit out of my knowledge nowadays, so to say.
Okay, thank you. Well, then I will ask a more specific question about your thesis.
Sure.
I was looking at conjecture 355 on page 65.
1 point.
And this is a conjecture about finite dimensional Banach spaces. Well, it's a conjecture still, I guess, so you haven't proved it. But when I was reading the proofs in previous chapters, previous paragraphs, I noticed that an important step you take there is by restricting the UMD space to a finite dimensional Banach space. And therefore, when I was reading this conjecture, I was wondering if you could prove it, would the extension to UMD spaces be possible?
Yes, so many thanks. So this will be definitely possible. The point here, why the space here is finite dimensional, is an existing now a certain Bellman function with some nice properties, which is better to work only on finite dimensions. In infinite dimensions, it becomes a bit bad, but when you restrict to finite dimensional, it's fine. But everything can be extended to infinite dimensions. In this particular case, because of some tricks. So if you have, say, a martingale, you have, well, here we have a conjecture about weak differential subordination. And what one has, okay, what one has in a general situation, what one usually does is the following. So assume that X is infinite dimensional, then one can restrict to find dimensions in the following way. One can consider a certain, let's say, a family of projections on X star. I'm not sure that it's a projections. No, family of certain operators on X star. And what you do the following. If you have a weak differential subordination of two martingales, then you just consider such martingales. You also have weak differential subordination with this. But I'm not saying what is this family about, but this is, say, now a magic family of operators. You consider these operators, then your martingales take value in finite dimensional subspace, in finite dimensional space, for which you say prove this conjecture. And then when you want to extend, you just use the following fact that, first of all, you use the fact that, use the following fact that expectation of norm of Pn star, let's say M, T, or with supremum, doesn't matter, it converges monotonically actually. Because you choose these operators in a very smart way. It will converge monotonically to your expectation of just mt to the power p in n, as n goes to infinity. Okay, and the same you have for m. So if you have some inequality for pn star and pm star for finite dimensions, and then you will have the same inequality for m and n in infinite dimensions, given you also can control the UMD constant. But because our operators are magic, you can control also the UMD constant on these finite dimensions. So you can, so to say, if you solve it for finite dimensional case, by using these family operators, you can extend it to infinite dimensions.
So this could have been a theorem in your thesis, that the conjecture, when proved, implies the same result in UMD spaces.
It could be a theorem or a proposition, but the point is that I used this type of techniques with this family of operators too many times in my thesis. So it's more like a remark.
Okay.
I wouldn't call it a theorem, but it's more like...
That's another thing that I noticed. I was wondering, it's a bit of maybe a critical point, but it's not meant like that. But so the fact that you can restrict to this finite dimensional space, that's some special property of these UMD spaces. It kind of seems like that's why the reason why they're so important, because you can do everything finite dimensionally and then kind of lift it, and that's only possible for these UMD spaces.
Also, yes. This is one of the important parts of the UMD property, yes. So here, I mean, I'm not saying what are these operators about, right? But while proving that the UMD constant for these fine dimensions is dominated by the UMD constant of the original space, you need to use this UMD property quite heavily, like some duality type of property of this. So yes, it's somehow a part of nice properties these spaces have, yes.
Okay. I think I have time for one more question. Yeah, a lot of places in your thesis use a function phi, which is called elementary predictable.
Mm-hmm.
And this elementary predictable function, it's like a simple function. At least it looked like a simple function to me. You have a finite number of vectors and a finite number of intervals for which they're constant, and so it's like a simple function in measure theory. At least that's the feeling I got.
Yeah.
But then, usually in measure theory, for example, these simple functions, you take a limit of them, and then you prove something for more general functions. And I didn't see that happen with these elementary predictable functions. So lots of statements are just about these elementary predictable functions, and then there's no extension to, well, whatever the limit would be of these things. Could you comment on this?
Yeah, good remark. So, you know, like in theory of say even or real analysis, if you have step functions, then you can extend some theorems to some functions, but not all functions, right? You can extend, say, if you have some LP bounds for step function, then you can extend it only to LP space, right? Space of functions with a finite pth moment. And here it's the same, so sort of the same. You have elementary predictable functions. It's not only just step functions, but also you have some predictability in order to make your stochastic integral a martingale. And then you have some estimate, and then you can extend it. And in some cases, actually, I got some examples here, like in chapter 9, where you have a general stochastic integration theory with respect to a general martingale, to which spaces you can extend. But this type of spaces, they vary. Sometimes it's just predictable functions having some properties, or sometimes, and I think that this is what actually was in the work of Mark Ferrer and Jan van Neven and Lutz Weiss, it's more than just predictable functions. You go outside. It gives you some, in their work it was, I think, some gamma-ordonifying operators which don't have representation of a function. So I think the point is that in many cases you can extend to something, but this something might be either too good or too bad, so to say, or none of them. So yeah, in particular, in chapter 9, you can see some type of extension.
Professor Kator, are you satisfied with answering so far?
Very much so. Thank you very much.
Thank you very much for your opposition. We're moving to this side of the room, and I would like to ask Professor Jongbloed to continue the opposition.
Thank you very much, meneer de rector. Waarde promovendus. So let me also congratulate you with your work. With interest, I read part of your work. I must say part of your thesis, because this is basically the first time I read a thesis where in section 1.5, actually there's mentioning of papers that did not get accepted for publication in the thesis. So it's really impressive. And sometimes also a little bit intimidating for somebody with my background. But we had a very interesting discussion also on the context of your thesis and the things that you have done, and also the achievements that you had, and that was very helpful also for me. Let me start with one very simple, short question, maybe related to these papers that did not get it into the thesis. So what was your reason to select these ones and not other ones?
Hoogelijk, the opponent, thank you very much for your question. So I sort of, yeah, I tried to put somehow the most fundamental results inside, though there was also another paper with Professor Mark Ferrer, which I didn't include, which was of 50 pages, something like that. which was also, I think, fundamental for learning all this theory. The other papers which I didn't include, they were, I think, contained minor changes or minor things which were not so fundamental, but just giving some sharper estimates or some giving some small moments, which are though important. So, for instance, that result which I already mentioned for the canonical decomposition, that the sharp norm bound for each part of the canonical decomposition coincides with the norm of the second order Riesz transform. This is something I didn't include here, though it's very important to have a sharp estimate, but since it was just a minor change of known techniques due to also Guy's Montgomery Smith Saxman paper and due to some other papers, I just didn't want to
spoil my thesis with these not so fundamental things.
Okay,
that's
though
that's
interesting.
Right. Yeah. You should say that certainly. But also maybe also connected to that, also with the question of Professor Dirksen. So he said, well, sometimes you go to a more general situation, and then if you look at the more general context, then sometimes you can prove the less general results more efficiently or with less assumptions, or maybe improve it a little bit, or, as you said, improving upon constants in estimates. Did you also see this, I mean, from chapter 9 to 8, I understand that something like that happens, that you could prove a more general, the result from a more general perspective. But did your work also lead to new insights or sharper constants in the more classical precursors of this work? Because the decompositions that you used were quite known already for some time, and you actually rejuvenated the research in that direction. But did it also, in the more simpler case, lead to new insights?
Thank you for this question. So somehow, if you consider some parts of my PhD thesis, it indeed gives some different insight concerning this question. So, for instance, if you work with this decomposition type of things, then, as I told, you should work with it like with the martingale transform of zeros ones, which I think actually people didn't work with like this, so to say. So this particular small thing gives you an insight how to work with this canonical decomposition. For instance, if you want to prove certain type of estimates, I'm now talking about very general estimates, and you want to use it using the so-called Bellman functions, so some very special functions which you plug in your martingale and they do all the job. And then this Bellman function highly likely should coincide with the Bellman function constructed for 0,1 martingale transform and the way back. So because you have some constructions somehow, some duality between them, some connection. So even in the real-world situation, I think this might be a very good insight if you work with such type of decompositions. Another thing, for instance, is in chapter I think 5 or 6, chapter 6 on orthogonal martingales. So where quite general estimates were proved. They were proved also for general Banach spaces, but who knows? Perhaps there are also new estimates for real value thing, and who knows, you might need these estimates even in the real value thing, which also seems to be new, at least for me.
So if you ask who knows, I would first ask you, but in any case. So maybe one very quick last question, because it puzzled me a little bit, and then it's also related, I'm sorry, to a proposition, and maybe I can ask you to read one of those proposition. No, meneer Director, I would like to ask a question about the proposition. I'm sorry for this. Proposition 9.
Proposition 9. Could you read out Proposition 9, please?
A proper Russian paper is like a square meter near the South Pole. Nobody wants to own it. Only a crazy one wishes to manage it. And one may need several wishes in order to reach it.
Thank you very much. So yes, so I was of course trying to think about the deeper thoughts that were behind this one and the proposition before this. And then I read the translation, and I thought I had some idea that the paper was a newspaper. But then I looked at the other side, and it seems to be a a scientific paper.
Yes.
Could you maybe help me in a few words how I can further elaborate on that when I'm on my bike?
Okay. Many thanks. 1 second. Yes. So, so this is, I would say, rather cultural and philosophical thing. You should read these propositions all together with proposition 8. So,
I guess so.
You should sort of compose these propositions. And this is more about how do people look, what is important for them, so to say. And what I found
But a scientific paper or a newspaper?
It was a scientific. It was a scientific paper. It was about a scientific paper, perhaps a newspaper as well. But unfortunately, I didn't have much experience working as a journalist. But yeah, this was about scientific paper, but not only about scientific paper, but I think also about this type of work, this creativity work, so to say, and things what are of importance for people from different cultures. I'm not saying that all Russian people are like this and all Dutch people are like this, but I'm just saying that this is the difference, that in Russia we have more people which sort of better discover Antarctica rather than New York, right? And Amsterdam is the other way around. And you have these different point of views, different type of values.
Okay.
And then this is something we need to accept. So
we need to accept it, and I have some food for further thought. Before you ask it, yes, I'm satisfied with the answer.
Thank you very much, Professor Jongbloed. Yes, we move now to the promotores to continue the opposition, and quite often the most unexpected questions come from the people you know best. I would like to ask Professor van Neerven to continue the opposition.
Dank u wel, meneer de rector. Waarde promovendus. First of all, I would like to extend my congratulations as well to the beautiful thesis and all the work you did. It's very gratifying to see you now defending this thesis after 4 years, which contains so many profound results, some of which we couldn't even anticipate asking ourselves to you. That being said, my question is mostly philosophical, maybe also a little bit historical. As you mentioned in one of the propositions, which I think in the interest of time we refrain from reading aloud, that you in these spaces are so important, and actually the most important in your mind and most flexible class of Banach spaces. Why did it take so long for mathematicians to actually identify this class? If you go back in history, well, then Banach spaces were introduced in the 30s, you could say, Banach. Hilbert spaces a little before, with the advent of quantum mechanics in particular. Martingales are also well established for a long time, and then there's a big gap, and then all of a sudden there's this UMD theory. So why did it take so long?
Hooggeachte promotor, thank you for your question. So, in my opinion, well, what was historically, I'm not sure whether it's true or not, but in my opinion, is that this probability word and function analysis word, they interact with each other and they work with each other from time to time, but perhaps it used to be not so close. So, I mean, there were experts, there were people which were both experts in both fields, but perhaps not as many. So, historically, it could be that this area of people who work in stochastic analysis, both with Banach spaces, this family of people, it became just too big, and then they developed this connection. Though there is connection with some geometry of Banach spaces, and then this is a bit of a mystery for me, why it wasn't developed before, why people with knowledge in function analysis didn't realize that a certain convexity or concavity property of a Banach space plays a role. This perhaps a bit of a mystery, but again, you see the main motivation goes from stochastic analysis somehow. So this what I will think about this, so to say.
Very much. I think in the interest of time, I have more questions, but I give back the word to you, Mr. Rector.
Thank you, Professor van Neerven, for your opposition. And finally, I would like now to ask Professor Van Aar to continue the opposition. in the time that's left.
Waarde promovendus, I of course had enough opportunity to ask you questions during the last 4 years, and I did ask you a lot of questions, and you answered quite many of them. So the proposition that I would like to ask a question about, if I may, is proposition numbers 3, 4, and 5. They are kind of related, but maybe it's enough to read proposition 3.
Yes, please.
There are no continuous martingales on the integrals with respect to a Brownian motion.
Thank you. So, so in this proposition and also the next two, you basically say that certain things do not exist, although your thesis is full of these things. So, could you please clarify what you actually mean with these propositions?
Hooggeachte promoter, many thanks for your question. So certain things do exist, no worries. But the point is that, and it actually goes back to your work, okay, it's now going to stop.
Thank you, Madame Biedel. I request the promovendus and the paranymph to take his and her seat in the audience again. The committee will withdraw now for further deliberation in the committee room, and the session is adjourned.
Numbers.
sorry for your glasses.
I'll just remove this. I think that
Yeah, just put your... Now you have to wait. How can they something like that?
I reopen this session and I request the promovendus and his paranymph to stand in front of the committee. Het College voor Promoties van de Technische Universiteit Delft, vertegenwoordigd door de hier aanwezige commissie, heeft na kennis te hebben genomen van uw proefschrift met stellingen en na uw verdediging daarvan te hebben gehoord, met inachtneming van het bepaalde in de wet op het hoger onderwijs en wetenschappelijk onderzoek besloten u de graad te verlenen van doctor en wel cum laude. Ik verzoek de promotor door het College voor Promoties als zodanig aangewezen zich wel van de hem opgedragen taak te kwijten.
Uit kracht van de bevoegdheid bij wet toegekend aan het College voor Promoties verklaar ik namens dat college, hier vertegenwoordigd door de rector magnificus en de overige leden van de commissie, bij deze u te bevorderen tot dokter. En u alle rechten te verlenen welke aan de dokterstitel zijn verbonden. Ten bewijze hiervan overhandig ik u het diploma dat u het recht geeft de titel dokter te voeren, ondertekend door de rector magnificus en de promotoren, en voorzien van het zegel van de Technische Universiteit Delft.
It is the promoter's privilege to be the first to congratulate the young doctor. Professor Naar, the floor is yours.
Dear Dr. Yaroslavtsev, dear Ivan, first of all, congratulations, or in your language, pozdravljaju, with successfully defending your PhD thesis and obtaining your doctor degree. I will take this opportunity to reflect on the last 4 years, not spending too much time in going all details, but okay, so in 2014, you contacted me if there was a PhD position available in Delft. And actually the connection was made via Sonja Cox, who is a professor in Amsterdam. And she knows your sister, who is also a mathematician and is working in Germany. So in November 2014, we invited you to come to Delft for a seminar talk. And our whole group was there because I told them you were a potential candidate for a PhD position. Your talk was about polynomials and Gaussian random variables, and it was definitely not an easy topic. You explained us how you solved an open problem during your master project guided by Professor Bogachev. If I remember correctly, the question was solved by you and your co-author by giving a large class of counterexamples. My colleagues and I agreed in 2014 you seemed a very talented young fellow, and it would be quite safe to let you start a PhD project in Delft. So you started in 2015 in March, and for several weeks you came with me to Utrecht to attend my lectures on stochastic differential equations. You spent a lot of time reading the books Jan and I, together with others, have been writing, which are now the infamous volume 1 and 2 of analysis in Banach spaces. And you studied a lot of papers on stochastic calculus and probability theory in infinite dimensions. And it was clear from the beginning that you really liked this topic. The problem I gave you in the beginning was difficult. The problem was find a version of the BDG inequalities for general martingales, or as general as possible, with values in the UMD Banach space. Of course, I also gave you some intermediate things to try at first. You had the crucial idea to rewrite a vector-valued continuous local martingale as a time-changed stochastic integral with respect to a cylindrical Brownian motion. This trick allowed us to complete our first joint paper within 1 year, and we basically established the full theory in the continuous setting. We were quite happy about this. The paper was accepted in a good journal, but of course the first question was not answered yet, and we wanted more. The paper did not make it to the thesis. We already talked about that at the defense, but this was for very good reasons. After the paper on continuous local martingales, you also got into contact with Sjoerd Dirkse and Carlo Marinelli. You have worked with them on stochastic evolution equations with Poisson-type noise, and this project is actually still in progress. And together with Sjoerd, you also started working on Burkholder-Rosenthal inequalities in LQ spaces and applied that to stochastic integration theory. And this has led to a really impressive paper, which was thoroughly discussed during the defense. You decomposed the martingale in 3 parts and somehow analyzed every part separately. I was quite happy that the continuous case, which we worked on together, was still part of that theory and was still useful. As a separate project, I suggested you to think about extending the work of Banuelos-Bogdan, who somehow considered Fourier multipliers, very special Fourier multipliers, and I wanted you to extend that to the UMD valued setting. Of course, an immediate problem was that the subordination of martingales that they use does not work in this generality. So I suggested that you might try something with functionals. That's, I think, the way I formulated it in the definition of subordination. Now something very special happened. After a week, you came back and completely solved the problem. You found a way how to prove LP estimates for what you called weakly subordinated martingales. In the discrete case, but also in the pure jump case at first. Also, you managed to apply this to extend fully the Banuelos-Bogdan paper. And I already knew that you were very clever back then, but this really impressed me a lot. You managed your way into the world of Burkholder functions in infinite dimensions and immediately get a highly non-trivial result. And after that, things went really quickly. You had many, many new results after that in a very short time period, and many things came together. Here you were mostly working on your own, and my only job was to encourage you and to give you some suggestions for future projects. I really enjoyed reading all your results on weak subordination and all the characterizations of UMD Banach spaces that you obtained, especially the ones for decompositions of martingales. Both results that I just mentioned are very natural and have been completely overlooked in the literature, say for more than 25 years. Finally, a bit less than a year ago, you solved the original question I posed in the beginning of your PhD, to find the BDG inequalities for general martingales. And first we solved this together in the Banach function space case, but then again something amazing happened. You solved the general case by somehow a completely different type of argument, which I did not even dream of being true. So this result was so strong that some of the earlier work could now be derived as a simple corollary. So that's really a great achievement. Your time as a PhD student must have felt like a great adventure. A lot of new mathematics, new people, a new country, but also supervising you has been a great adventure. You completed a large amount of work in the world of UMD spaces, a large part of which was completely unforeseen. Sometimes supervising students can be a lot of work because as a supervisor, you need to solve a lot of mathematical problems, daily life problems, many things. In your case, the supervision was a lot of work because of very different reasons. There were so many results I had to read and proofread that was really incredible. Of course, this was delightful to do. You have been very kind to the committee members by not including all your results in the thesis. So your visits to London, Bonn, Warsaw, Uvescola, they played a huge role in your project. And it's great that during some of the visits, important collaborations got started. Traveling did not always go so smoothly. There was, of course, always the struggling with visa as a Russian citizen. Also, bike riding was something you had to get used to in the Netherlands. But also you had a very special once-in-a-lifetime experience during your world trip to Canberra, Sydney, and in particular, Seoul. But maybe we discuss that in more detail later this day. During the last 4 years, it turned out that time time changes is one of your favorite tools. But now times will be changing for you again. You have gotten an offer to work at the famous Max Planck Institute in Leipzig as a postdoc researcher. This is really a great opportunity, and I'm sure you will learn a lot there, and hopefully you will learn about new interesting research directions where you can demonstrate your problem-solving abilities, and hopefully you can connect also to the research you have done here. I'm sure that your wife and you will enjoy living in Leipzig. The day is not over yet. It's actually still quite early because it's an early defense, and I'm looking forward to the rest of the day. The weather is not so good, but I hope everyone will manage, and in particular that all the return flights will not be cancelled. There was some problem yesterday. So, Ivan, I really enjoyed every second of your stay in Delft, both professionally and personally. And I wish you all the best during the next episode of your life, and I'm sure that we will stay in close contact. All the best from your advisor, collaborator, promoter and friend.
Learned Dr. Yaroslavtsev. You now have the right to use the title of doctor. Your doctorate means that society can rely upon your judgment, that you will act transparently and communicate independently about your results and the social relevance of your work. In other words, your doctorate implies that you will uphold scientific integrity, and I wish you a great deal of wisdom and prosperity with your new degree. On behalf of the Board of Doctorates of Delft University of Technology, I congratulate you and your family on earning your doctoral degree. Dear Dr. Yaroslavtsev, sorry, I need to practice. You may return to your seat. Ladies and gentlemen, I thank you for your presence. I hereby close this academic session.